I'd like to begin by thanking the organizers for inviting me to this very nice conference. This is my first time in Houston. I'm originally from Calgary, which is the Canadian equivalent of Houston. So it's very interesting to see the American counterpart for the first time. So I'm going to be talking today about how to compute the multipartite entanglement in a quantum material, not using the spin response as you've heard up to now, but trying to use the single particle response. In particular, I'm interested in connecting multipartite entanglement to spectroscopies like that come from angle resolved photo emission and standing tunneling microscopy. So this will be an outline of my talk. I'm gonna insult your intelligence by first telling you what multipartite entanglement is, but it's maybe useful because just to orient you in terms of what it means for a spin system versus what it means for an itinerant electron system. Then I will tell you how to connect the multipartite entanglement to spectral functions, such as one encounters in STM and ARPES, and the vehicle by which the connection is made is the quantum Fisher information. And it turns out that you can't just use the standard recipe for connecting the multipartite entanglement to a single particle Green's function that's used in neutron scattering. You have to be a little bit more clever. The standard method doesn't work. And so in this third part of the talk, I'll tell you how one can adapt the approach to single particle spectroscopies. And what you'll see is it involves this doubling trick, this fictitious doubling of the system. That will be one aspect of it. The other aspect will be taking into account symmetries. Up until now, the quantum Fisher information bounds that you've seen do not take into account any symmetries of the supposed symmetries of the system. So for example, in these spin chain systems that have been studied, nominally they have an SU2 symmetry. That SU2 symmetry has not been exploited. And so here, in order to get it to work, the recipe to work for this single particle Green's function, you'll need to take into account symmetries, and you'll need to take into account the fact that the overall electron number is conserved. So let me start with the definition of multipartite entanglement. So the multipartite entanglement, you can say, well, it basically refers to the ability to factorize a wave function into blocks. You can say that if you have this wave function factorized into k blocks, you can say that the wave function has m partite entanglement if these various k blocks don't contain any more than m sites, and at least one of the blocks contains exactly m sites. So in terms of what this, just to orient you in terms of a spin system, this is a spin wave function that has it's a 5-site spin system, and it has 2-partite entanglement. You can see that the first 2 sites are entangled, sites 3 and 4 are entangled, and then site 5 is just hanging out by itself. In terms of what it means for an itinerant electron system, if you had creation operators governing 5 different modes of the electrons, mode 1 and 2 are entangled, modes 3 and 4 are entangled, and then 5 is all by itself. So this 5-site itinerant electron system has again 2-partite entanglement. Now, yes. Yeah, so that's maybe I can answer that in a more general way. What you mean by how much multipartite entanglement a system has really depends on the definition of the degrees of freedom that you're considering. So, for example, if I looked at a Fermi sea of electrons and I looked at them in terms of K space, that has that has 1-partite entanglement. Whereas if I looked at it in position space, it would be fully entangled. So you really have to define what you mean by your degrees of freedom when you talk about multipartite entanglement. So yeah, so doing non-trivial transformations of degrees of freedom like Jordan-Wigner can really change the answer that you get. So of course, we're interested in multipartite entanglement and entanglement measures in general for fundamental reasons, but there are certain things, suppose you were talking to a program manager at some funding agency, there are certain things that multipartite entanglement buys you. It buys you improved measurements and sensing. It's not surprising it buys you improved measurements since the quantum Fisher information is a notion from quantum metrology. It also buys you improved quantum networking schemes and improved quantum error correction schemes. So multipartite entanglement you can think of as a resource that you can exploit in various quantum technologies. Now, of course, as we know, we're going to be using the detect bounds on the multipartite entanglement. We're going to be using the quantum Fisher information. And what really, I would say, well, at least maybe I can just phrase it personally, what got me interested in using the quantum Fisher information to extract information about multipartite entanglement was this 2021 paper involving Ellen Shai and Alan Tennant, where they were able to take old neutron scattering data on potassium copper trifluoride, which is a one-dimensional spin chain. They were able to take these old neutron scattering measurements and convert this into a bound on the amount of multipartite entanglement in the system. And it was published 2021 in Physical Review B. And they were able to argue that they saw up to 4-partite entanglement in the spin chain. So this is what got me interested in this problem. So in this part of the talk, I'm just gonna actually discuss in some detail the quantum Fisher information, because I think it's important to understand some of the details surrounding how one connects the quantum Fisher information to bounds on the multipartite entanglement to understand what I'm doing in terms of connecting the QFI to single particle spectroscopies. So I already said, the quantum Fisher information is a notion from quantum metrology. It basically tells you how sensitive a state is to a unitary rotation. So if I have some unitary, which is defined via some Hermitian operator, and a parameter theta, and I apply my unitary to some density matrix, resulting in another density matrix that's a function of this angle theta. The question is if I do a single measurement, how accurately can I determine the angle theta? And so what the quantum Fisher information, it gives you a bound on the variance of your guess of this angle theta. So the larger the quantum Fisher information is, the tighter the better accuracy you can measure infer this angle from a single measurement. And so as a simple example, you could imagine taking a spin, applying a magnetic field for a certain amount of time and for a certain amount of unknown time. And you could ask, well, if I do a single measurement, how long of time has that magnetic field been applied to? And the QFI will give you a lower bound on the variance of that measurement that tells you what the time of the application is. So we'll just skip that. So as Matteo already mentioned, the QFI for a pure state has a very, very simple form. It's just the variance of the Hermitian operator A relative to the state. And in general, the more multipartite entanglement the state has, the larger the QFI is. However, I think that the state can have lots of multipartite entanglement, but the QFI doesn't need to be large. Yes. So yes, if you choose a bad operator, you're going to get a very small QFI. So yeah, the choice of operator is very, very important for detecting multipartite entanglement. You make a bad choice of the operator A, you could detect nothing. It doesn't mean it's not there. Remember, the QFI is only providing you with the lower bound on the entanglement in the system. So a bad choice will just means that this lower bound will be smaller than it need be. That's the next slide. Yeah, so of course it matters. The normalization of A absolutely matters because you could just scale the A by a scalar and you could make F as big as you want. So you have to, obviously in determining the bounds, you have to know what the normalization of A is. And so, yeah, in the previous work, the normalization was always assumed to be unity, or the spectral bounds, the eigenvalues of the operator were assumed to be the, here, we'll go to the next one. Sure.
So if there's the limit on the spectrum of A, then there's the limit on S, right?
Yes.
It cannot go
Yes.
bigger. So all these divergences that we saw.
Well, really,
it not have operators that have a limited spectrum.
no, they do because so for a spin chain, those divergences as you went to zero temperature were being cut off by either a log in the temperature or a log in the system size.
But so then A, the operator A probably has a spectrum that's not limited by one.
Well, here, so let me just go to the next slide. So here, it's typically what you do when you're considering the QFI. Your operator A is defined as some sum of local operators, where the sum is over all of the sites of the system. And then the spectrum of each operator defined on a single site is bounded by this H min and H max. So for the SZ operator, it would have been bounded by, -1/2 and 1/2. So of course, the overall spectrum of A is not bounded as you go to the thermodynamic limit, but the relevant bounds are on AI, these single site operators. And so if the bounds on the individual AIs are HI and H min, then the condition, what the QFI has to satisfy in order to detect M+1 partite entanglement is this expression. It's M times the sum over all of the sites of the square of the difference of the individual spectral bounds on the operator's AI. Now, again, this is in some sense, a very crude bound because it does not include any symmetries of the wave function. It's basically allowing for all possible wave functions. It doesn't include, you could, for example, with these spin chains, that you have, well, if it was an XXZ chain, you would have at least a U1 symmetry. If it's a Heisenberg chain, it has SU2. So you could lower these bounds if you took into account symmetries. But of course, that makes the calculation a lot more complicated. So this does have the virtue of simplicity. But why I'm stressing this is that for the single particle spectroscopies, when we connect the QFI to entanglement bounds, we're going to have to use symmetries in order to get anywhere. So that's the QFI for at zero temperature, at finite temperature, or for any mixed state where you can write down the density matrix in this form. The QFI takes this form involving the eigenvalues of the density matrix. This was an expression that Matteo already flashed. And just to
but then we get rid of the black line top of the slide.
I'm not sure how to do that. I don't see an OK button on my own. Sorry. Yeah, I would happily do that, but I don't see it on. Yeah. Yeah. Okay. If you're interested in learning more about the QFI, I would recommend this review article by Pezzi and Smertzi, which appeared in this rather obscure proceedings, but it's also on the archive from 2014. So this has a very detailed discussion of issues related to the QFI. So I found this to be a very useful reference. But if you take this general formula for a mixed state and presume that the mixed state is thermal, then you get this formula that's been flashed many times where the QFI is expressed as a weighted integral over the imaginary part of some retarded Green's function. of time. So you need to move along. So just to reorient you, in terms of the notation here. So for neutron scattering, you would choose A to be the sum over SZI, and then the quantum Fisher formation takes a weighted integral over the dynamical spin response function. And again, the Alan Shai and Alan Tennant were able to, and collaborators were able to infer that that the potassium copper trifluoride had at least 4-partite entanglement. So let's turn to how one adapts this methodology for single particle probes. So in particular, I'm going to be interested in connecting to the single particle Green's function that you would measure using scanning tunneling microscopy or angle resolved photoemission. And the first thing I want to show you is that sort of the naive choice of the witness operator fails if you were just following the neutron scattering approach, you might think you could take your operator A just to be a sum over the local fermionic creation and destruction operators. Here, I mean, one of the conditions on the operator A, sort of built into the whole QFI methodology, is that A has to be Hermitian. That's why I take CI dagger plus CI. So it's very easy to see the spectral bounds for this operator are -1 and 1. And so if I want to detect using this particular witness operator built from single particle creation and destruction operators, the QFI has to satisfy this inequality in order to detect M+1 partite entanglement. However, it's not very hard to see that no matter what wave function you have, the QFI will actually, if you actually just go ahead and compute this formula, you'll see that the QFI has to be less than 4 times the sum of these AIs. So what that means is that for this not such great choice of your witness operator A, you're never going to detect any entanglement. So that's not good. And what it means is that we can't just mimic what was done with neutrons. We have to be a little bit more clever. And so what being more clever here amounted to was a doubling trick where we create 2 copies of the system. And so I can go through very quickly how this doubling of the system works in a very simple case, a 2-site system. So imagine that we have 2 sites, and we don't need to think about the 2 sites in terms of some Hamiltonian, but we can imagine that there's some hopping Hamiltonian and an interaction term in the Hamiltonian for this 2-site system. So we double it. So now we have copy A and copy B. And so we have a Hamiltonian for copy A, and we have a Hamiltonian for copy B. The copies do not talk to one another. I mean, the Hamiltonians of the copies do not talk to one another. They're otherwise identical copies that do not interact. But what we do is we choose our witness operator, which of course we are free to do however we want, to interact between the 2 copies. Particularly, we choose A to hop between copy A and copy B. And this has the virtue that A, instead of being a fermionic operator, which was the origin of the failure of the naive choice, it's now a bosonic operator, which makes life better, as you will see. So does this doubling trick together with this particular choice of witness operator that hops between copies actually detect entanglement? It does if you also suppose that symmetry is a good quantum number. So, or that we have symmetry and overall electron number. So that if you suppose that the wave functions are eigenstates of the overall electron number. So to show this, let's consider states with 1 electron. So there's 3 possibilities. You have a state where 1 electron sits in site 1. We have a state where 1 electron sits in site 2. And then we have a state which has 2-partite entanglement, where the 1 electron is indeterminately situated between site 1 and site 2. So let's go ahead and compute the QFI, we double the system, which just means taking a product of our state for the doubled system is just a product of the states for each individual system, and then we just go ahead and compute the QFI for our witness operator, which is a trivial task. And what we see is that for the two states which only have one partite entanglement, the QFI is identically 0, whereas the QFI for the third state with two partite entanglement is not necessarily 0. So we can simplify this calculation. We looked at the state with the most possible entanglement, where the electron sits equally on site 1 and site 2. Then the QFI for our doubled witness operator takes this form. And if we choose these coefficients A1 and A2, which we use in the construction of our witness operator, which are arbitrary, we're free to choose whatever, provided we choose A1 to not equal A2, then the QFI for this third entangled state is non-zero. So the lesson is that if the QFI is 0, then we have one partite entanglement. If the QFI is finite, any non-zero number, it has two partite entanglement. So we generalize this now to n sites. We move away from our two-site model, and we define our witness operator again in this doubled system to be this hopping operator between copy A and copy B. And in particular, we're going to look at a set of witness operators that are indexed by this wave vector K, which is basically, so the coefficient is just the plane wave corresponding to this wave vector K. And we are again going to suppose that electron number is a good quantum number. And one important aspect of this is, so a difference that I'm advocating is to look at the QFI, not just for a single witness operator, but for a whole set of witness operators simultaneously. And that way you actually get more information. You can, as I'll show you very briefly, that you can not only detect whether there's a certain maximal block of entanglement in the system, but whether there's some sort of entanglement pattern in the blocks. So for example, if you had an 8-site system, you're going to be able to using the information coming from the witness operators for all K, you're going to be able to tell if or if not there's a block structure of 4 sites entangled times 2 sites entangled times 2 sites entangled. So you're going to be able to determine not just whether there's a block of 4 sites and 4 electrons entangled, but whether there's a particular overarching pattern. So you're going to get more information by looking at all of these witness operators simultaneously. Now, on this slide, which is rather busy, but it's maybe the key slide of the entire talk. If I take my doubled witness operator and I try to express the QFI in terms of the single particle Green's function, this is what I get. So here's the same formula that you've seen before, the QFI being expressed as the imaginary part of some retarded Green's function. Here, the retarded Green's function is of this doubled witness operator. And if you just go ahead and do the algebra, you see that this function S, which is what you're doing the weighted integral over when you compute the QFI, this function S is basically a weighted convolution of the single particle spectral function. So what this formula allows you to do is that if you've measured the single particle spectral function, which is what you do if you do ARPES or STM, you can just take your formula, you can just take your measurement and you can plug it into this formula and you can get an expression for the QFI and so a bound on the entanglement in your system. Of course, that's maybe a little bit glib because I'm a theorist. You have to worry about normalizations, of course. Normalizations are important, and that can be hard, particularly if you had this complicated multi-band system. But if you had a system with an isolated band, getting the normalization right should be easier. I won't say pretty easy. Yes. Yes. Yeah, so yeah, the sum rule for the single particle spectral function, the way you would set the normalization would be the sum rule comes down to the anti-commutation relation of the fermionic operators. Well, so optical conductivity is a two-particle response, so it'd be different in that sense. Well, no. So the reason why you see two versions of the spectral function, single particle spectral function coming in is coming from this fictitious doubling of the system. That's why you have two copies. But so there's, yeah. So one disadvantage, I've got 0 minutes, but I've got just 1 or 2 more slides. So one disadvantage is that in the original, in all the work that you've talked about up to now, the computing the bounds was very, very simple because the bounds in the QFI were just connected to the bounds of the eigenvalue spectrum of the single site operators. Once you take into account symmetries, which is what we're doing, total electron number is a good quantum number, you have to compute the bounds by brute force numerics. You have to actually maximize the QFI over all possible wave functions that respect the symmetry. So you can do this numerically. It's a bit tedious, but you can do it. And so this is what we've done for this 8-site system. And so we plotted the QFI maximums in this plot as a function of the K parameter parameterizing the witness operator. And we've given the maximum possibles for different possible entanglement patterns on the site. So this is an 8-site system, so we have 8-partite entanglement, the maximal possible entanglement, but we also have we've considered an entanglement pattern which the wave function is broken into two 4-site blocks, and then the other possibilities. So this is a sort of this relates to my promise that I'm not interested in detecting whether there's a certain maximal entanglement block in my wave function, but I'm interested in detecting entanglement patterns. Now, I'm doing this for an 8-site system by just brute force numerics. And of course, in the real world, systems, quantum materials that I'm really interested in connecting to are thermodynamically large. However, because of the QFI has a certain additivity property, I can take these results that I've done for the 8-site system and scale them up. So if I imagine I have a system set of 8 sites, but 8 times K sites, where K is arbitrarily large, and I'm interested in detecting an entanglement pattern in this system that involves blocks of 8 sites being entangled, then I can use my 8-site calculation, and the results are identical apart from a scale factor of related to the system size. So I can use these results that I've derived numerically for a finite system and scale on. That's the most important thing. And then we can actually just test whether we can detect entanglement in a particular in a wave function in the ground state of a particular model. So we chose this spinless fermion model, which has a hopping term and some interaction term, and plotted in blue, in this light blue color, is the QFI for the ground state at u equals 6 for this Hamiltonian. And you can see that we can exclude all possible entanglement patterns for this ground state wave function. But so the wave function either has 8-partite entanglement or 4 + 4-partite entanglement. Yes, Marcus. Sure, absolutely. But the QFI only provides a lower bound on the entanglement. I mean, so for in these Heisenberg spin chains at zero temperature, we know, because I can solve it by beta ansatz, I know, so I can write down the exact wave function. No, you don't. So the issue here is not whether you theoretically believe that there's a certain amount of entanglement in the system, it's whether you can experimentally detect it. That's, you have to, I mean, there could be all sorts of things going on experimentally that might make these theoretical calculations invalid. So if you actually want to certify that there's a certain amount of entanglement in the system, this is one imperfect way of doing it. But it's really, I mean, the QFI, I mean, we know theoretically, theorists, that there's a certain amount of entanglement in the system. But if you want to experimentally verify that, then you have, I mean, this is the recipe, using the QFI to connect entanglement bounds with spectroscopies that are experimentally accessible. So just like you've seen in the for the neutron scattering, we can compute the QFIs as a function of temperature, and as with neutrons, the QFI decreases as temperature increases. So your ability to use the QFI as temperature goes up as a detector of entanglement degrades. So that's not particularly surprising. So that was the minus 5 minutes. So here, let me my collaborators. So these are my collaborators, both on this project and on a project where we're exploring how to turn RIX spectroscopies into measurements of entanglement. And so there's on the top are the various theorists that have been involved, both at Brookhaven and Zucchi waves at Stony Brook. And then there are some neutron scatterers, Igor Zizhnak and Lazar Kish at Brookhaven that I've been working with on this project, and then a set of X-ray scatterers, which include Mark Dean, Matteo, and two of Mark's postdocs. So with that, let me just flash the summary slide. I won't go over what I've just said. I will advertise on this bottom bullet point that we have been working on how to convert the resonant inelastic X-ray scattering response into estimates of multipartite entanglement. And here, there's another tech, I mean, when Matteo was talking about using RIX to compute multipartite entanglement, bounds on multipartite entanglement, he was using RIX when it reduces to the measurement of the spin response. However, you can also take the full response of RIX, which is a much more complicated response function, and it turns out that it's non-Hermitian, the equivalent of the A operator that I was showing, which is in the formalism has to be a Hermitian operator. For RIX is not, so you have to do some work to get around this fact, and you can look at it at this archive paper. Okay, thank you for your attention, and sorry for going over.
Thank you very much, Robert, for a very nice talk. While we switch to our next speaker, yes, question, please.
So if you consider 4 completions of your system, would you get a little better?
It's possible. So I haven't checked this, but yes, there's all sorts of games you could play using multiple copies. I think the key thing is that you want to build a witness operator that's not fermionic, that it's bosonic. So if you had 4 copies, you could imagine